A very good evening to Bonjour and welcome. First, let me introduce myself. My name is Hong Liang, and my group member is Guan Sheng, Kok Kai Lin, and Loo Ji Yu. We are very excited to speak and share to you about our topic today, the carbon-carbon composite. And we divided our content into 4 parts. First one is the introduction, the second one is the properties and the application, the third one is the fabrication, and the last one is the advantage and disadvantage. First, I want to start our presentation with introduction of composite and the introduction of the carbon-carbon composite. Composites are becoming the important part of today's materials due to the advantage, for example, corrosion resistant and faster assembly. They are used as the material in making aircraft structure, electronic packaging to medical equipment, and space vehicle to home building. They can be defined as materials that consist of 2 or more chemically and physically different phases separated by a distinct interface. The purpose of the composite is to allow the new materials to have strength from both materials and oftentimes covering the original material's weakness, and also to obtain a more desirable combination of properties, for example, low density and high strength. On the basis of the matrix phase, composite can be classified into the polymer matrix composite, metal matrix composite, ceramic matrix composite, bulk metallic glass composite, and also the carbon-carbon composite. The composite generally have 2 phases, matrix phase and dispersion phase. Matrix phase can be called as the primary phase. It's a continuous materials constitute which holds the embed phase in place by enclosing the composite and help to provide the bulk form of the part. Besides, it also helps to transfer stress to the dispersion phase and to protect the dispersion phase from mechanical damage and chemical attachment. For dispersion phase, it's embed the matrix phase and help to reinforce the matrix phase by different geometry, for example, particle size, distribution, and orientation to achieve the desired properties. Therefore, this is sometimes called reinforcement. Dispersion phase can be in the form of continuous fiber, short fiber, whisker, particle, or wire. There is also an interface between the matrix and the dispersion phase in the composite materials. It is to create a bond between the phases for the composite to operate effectively and to control the overall performance of the composite. It also helps to transfer the stress from matrix to reinforcement. Now I want to introduce the carbon-carbon composite. It's also known as the carbon fiber reinforcement carbon composite, CFRCC. It consists of carbon fiber embedded in the carbon matrix. The continuous carbon fiber are used as the reinforcement to maximize the strength and toughness. The terra emerge of the carbon fiber in standard orientation within a continuous carbon matrix is used to achieve the desired properties. The carbon-carbon composite is in high fracture toughness and wear resistant, but the most attractive property of the carbon-carbon composite are their high specific strength and modulus, with increasingly being considered for aerospace application.
My name is Kok Kai Lin, and now I would like to talk about the properties and the application of carbon-carbon composites. In these composite materials, the carbon fibers provide strength, stiffness, and fatigue resistance, while the carbon matrix holds the fibers together. A synergistic effect also exists between the fiber and the carbon matrix, causing the composite to have relatively better properties than polycrystalline carbon. This table shows the comparison of properties between monolithic carbon and reinforced carbon-carbon composites. It shows that carbon-carbon composite has relatively higher fracture toughness, specific strength, and modulus of elasticity as compared to polycrystalline carbon. Another unique property of carbon-carbon composite is that its strength can be increased with temperature. This figure shows the strength properties of several carbon-carbon composites and other materials over a temperature range. The strength of advanced types of carbon-carbon increases with the temperature up to at least 2000 degrees Celsius. The increased strength is due to the closing of microcracks in the interface between the carbon matrix and the fiber matrix when temperature increases. In addition, they are able to retain their mechanical properties up to 3000 degrees Celsius. There are several remarkable properties of carbon-carbon composites, including low coefficient of thermal expansion, high thermal conductivity, low density, and excellent thermal shock resistance. For the application of carbon-carbon composites, they are increasingly being considered for aerospace applications as they can maintain their properties even at high temperature. They are able to maintain stable mechanical properties to temperature approaching 3000 degrees Celsius. Carbon-carbon composite is also used in aircraft brake pads due to its low weight, high wear resistance, and high temperature properties. In addition, the aircraft brake disc material should have high strength at elevated temperature and thermal conductivity to rapidly remove heat from the contact zone between the disc surface, and thus carbon-carbon composite is a great choice for this application. Next, carbon-carbon composite can be used for rocket nozzles production. Materials for nozzles should be able to perform uniformly to provide the required accuracy and range. It also needs to withstand an extremely rapid temperature increase in a highly corrosive atmospheres while maintaining a high degree of integrity. For commercial application, carbon-carbon composite can be used in furnace fixturing, heat shields, load plates, heating elements, and X-ray targets.
Hello, my name is Guan Sheng, and I will talk about the fabrication of carbon-carbon composite. This figure shows the fabrication of carbon fiber reinforcement. In order to fabricate carbon-carbon composite, we need to make the carbon fiber reinforcement first. For carbon fiber reinforcement, 90% of precursor used to make carbon fibers are polyacrylonitrile (PAN), while the remaining 10% is made from rayon or petroleum pitch. All of the raw materials are organic polymers, characterized by long strings of molecules bound together by carbon atoms. The process is split into a few parts like stabilizing, carbonizing, surface treatment, and sizing. The first part of this fabrication method is stabilizing. The precursors will be drawn into long strands or fibers and then heated at 200 to 300 degrees Celsius for 30 to 120 minutes. This causes the fibers to pick up oxygen's molecule from the air and rearrange their atomic bonding pattern. The fibers will be chemically altered from linear atomic bonding to a more thermally stable ladder bonding. After stabilizing the fibers, then the fiber will undergo carbonizing, which will heat the fibers to a higher temperature, which is at 1000 to 3000 degrees Celsius in a furnace filled with a gas mixture that does not contain oxygen for several minutes. The furnace is kept away from oxygen as the gas pressure inside the furnace is higher than the outside pressure, so that the furnace is sealed from oxygen entering. When the fibers are heated at high temperature, it will cause the atoms in the fiber to vibrate violently until most of the non-carbon atoms are expelled in the form of various gases. At about 2500 degrees Celsius, the fibers undergo graphitization, which is the non-carbon elements like O, N, and H will volatilize and result in enrichment of fibers with carbon. After the non-carbon atoms are expelled, the remaining carbon atoms will form tightly bonded carbon crystals. They are aligned more or less parallel to the long axis of the fiber. Next, the surface of the fibers after carbonizing will not bond well with epoxies and other materials if used in composite material. So the fibers will undergo surface treatment to improve its bonding properties. The fibers will be slightly oxidized by immersing the fiber in various gases such as air, carbon dioxide, or ozone, or various liquids like sodium hypochlorite nitric acid. The addition of oxygen atoms can provide better chemical bonding property and also roughens the surface by etching for better mechanical bonding property. After the surface treatment, the fibers will undergo sizing to protect it from damage during winding or weaving. The coating materials need to be compatible with the adhesive used to form composite materials. Examples of coating materials are epoxy, polyester, nylon, urethane. Lastly, the coated fiber will be wound into spools and can be used for further processing.
Hi, my name is Loo Ji Yu. Fabrication of the composite involves high temperature processing to pyrolyze the matrix precursor or for the reaction of gases to form carbon matrix in a chemical vapor CVD process. Composite can be further heat treated to graphitize the carbon matrix and carbon fiber reinforcement. Through graphitization, it chemically and thermally stabilizes the composite for the use at high temperatures. Now I will discuss about the advantages and disadvantages of carbon-carbon composite. Carbon-carbon composite have many thermal and mechanical properties required by aerospace material and that must be operate at high temperatures. The aircraft brakes that made of carbon-carbon composite are found to have remarkably stable frictional characteristic to have high temperature well above 2000 degrees Celsius. Carbon is stronger at 2000 degrees Celsius than at room temperature, while steel melts at 1600 degrees Celsius. The carbon fibers also provide the resistance to thermal shock that is so important in this application. Aircraft brakes made from carbon-carbon composite are relatively lighter than the brakes made of steel. The carbon-carbon composite brakes weighing 30 kg and compared to the brakes made of steel are 100 kg, and carbon-carbon composite found to be 3 to 5 times better than the brakes made of steel in actual number of landings before burning out. Thus, carbon-carbon composite brakes provide more than weight saving alone and perform better. Now for the disadvantages. Using carbon-carbon composite are expensive to fabricate and costly to machine into final product shape. And because of their high cost of manufacturing, causing them expensive for many aerospace applications where otherwise they are well suited. Carbon-carbon composite will suffer severe high temperature oxidation, which will result in the rapid degradation and erosion. When heated above 350 degrees Celsius, the carbon is susceptible to oxidation and the oxidation rate rises rapidly with temperature. Thus, in the presence of air, the carbon-carbon breaks down. That's all from our group. Thank you for watching.